Previous lesson we talked about the double integral and how we derived it and basically what it means. Well, to recap, it gives us the volume of the solid that is defined by the x and y plane and the curve, and the surface z equals to the function of x and y. So basically, now what we want to do is we want to find a way to find out or calculate what the double integral is, because it's sometimes more difficult to go through the limiting process. But before we do that, we need to develop a kind of new way of integrating. It's not entirely new, but basically it's something a bit foreign to us, and it's something that we need to use when we are dealing with two variables. Okay, so today's lesson is about evaluating that double integral, but before we do it, let's learn some new techniques on on a certain new integration. Okay, some properties of the double integral. Before I forget, for formality's sake, I think we should just go through it. It's basically the same results that you have for one variable calculus. Okay, you've got a double integral of the function c, which is a constant, multiplied by the function, okay, with respect to area over r. You can just simply bring the constant out. Okay, there's no surprise about that. Okay, the second result is that if you want to take the double integral of two functions, which is add or minus, you can take the double integral separately. So the double integral of f plus g or f minus g over the area r is going to be equal to the double integral of f over r plus the double integral of g over r. Okay, applying the double integral inside the functions, no surprise. Now the second one's a bit interesting result, but one doesn't need to take too long to understand it. It basically, because r, remember, r is the region, or is the area that is in the xy plane. Okay, now another geometric to reinforce our understanding. Okay, the surface z equals to the function of x and y. So r, if one may use such terms, is basically the projection of the surface onto the x and y plane. See, the r really gives us the area of the base of the solid for which the volume is what we want to find. So what this certain result tells us is that for a certain area r, we can really divide it into r1 and r2. So we can just divide it to r1 like that and r2 like that, and find the volume separately, okay, and add them up. Okay, that's basically what the result is. A basic geometric argument. You should be able to understand what it means. Now, why is this useful? Well, because sometimes the surface goes below the x and y axis. So basically, a good choice of the region R is important. Okay, I re-emphasize again that we're integrating with respect to the area, not with respect to the axis, as one variable calculus leads us to believe, or leads us to do. So, what is this new integration? Well, see, we are moving to integration of two variables. Now, as you know, if I'm asking you to integrate a function with respect to two variables, you may get a bit stunned. So, what we're going to do now is we're going to learn something called partial integration. Now, personally, I don't like the term partial, okay? Henceforth, we would, after we get a full grasp of the techniques, we would just use integrate with respect to something, okay? But basically, for formality's sake, it's actually called partial integration. Well, what does it say? Okay, it says that if we integrate from a to b of a certain function, okay, in terms of x and y, so this function in terms of x and y is a two-variable function with respect to x. What it means? It means that we're going to hold x fixed and integrate with respect to x. Sorry, we're going to hold y fixed, integrate with respect to x. The function is in terms of x and y, but we're integrating with respect to x, so we're going to hold y fixed. What does this term mean? Well, basically, okay, it means think y as a constant. And if you're familiar with Greek alphabets, let's just say alpha. That's what it means. Now, it's whole y fixed because honestly, y is not a constant. We can't really say treat y as a constant, even though you can think that way when you do the integration, but actually just whole y fixed. Okay, so if we integrate from a to b as a function of x and y, okay, with respect to y, what it means that you hold x fixed, integrate with respect to y. Okay, the variable you hold fixed is the variable that you're not integrating with respect to. Okay, very easy to understand. Okay, now this is the crucial part. I just want to contrast this with, okay, let me just erase this board. Oh, actually I don't need to erase the board. This is good. Alright, now, the double integral, remember, is this thing over here, right? The double integral is one over here. Now, this is not an iterated integral. Why do I say that? Well, basically because we have not explicitly defined what R is, okay? This is basically just something conceptual, okay? I mean, it's not something conceptual, but we know in terms of graphically what it means. Is like I said, the area R, okay, and we're going to find the volume, and the function is the surface, okay? This is not an iterated integral. What an iterated integral is something where the limits are explicitly given and we know what we are integrating with respect to. So an iterated integral, or basically repeated integral, is something of this form. Okay? Now it's quite obvious for you because you see what we know what to do. We know exactly what to do. We're gonna integrate first from a to b, okay, of the function x and y with respect to x. So now it's with respect to x, so we hold y fixed. We integrate that first, and whatever result that we get, we're gonna integrate that from c to d with respect to y. Okay, that's all it means. The iterated integral. Now, we have not touched on the theorem yet, which is going to be the next lesson. To move from this integral, the double integral, to the iterated integral, we're going to find that later soon. But what we want to do is basically for all our calculations, once we reach the iterated integral, we're pretty much safe. Okay, we are moving from the conceptual or from the geometrical to the calculations or the algebraic calculations. And from here, we can integrate immediately using partial integration. That's what it means. Okay, for this one, it's the same thing. I will not waste any more time. It's basically, you can just put a bracket over here. Just integrate the function x and y with respect to y, and then integrate from a to b with respect to x. Okay, so let's just go through a simple example. Very simple indeed. Okay, actually, I think you should be smart enough to know what's going on. But never mind. Let's just go through an example. Okay, integrate 0 to 3, 1 and 2. Okay, 1 plus 8x and y with respect to y first, and then with respect to x. Okay, so what do we have? Sorry about that. What do we have right here? Now, I would normally want to write the whole thing full, so I don't want to, really skip any steps, right? I'll put integrate 0 to 3 first because basically I'm looking at this one over here and I'm just focusing on the one inside. So I'm going to partial integrate, this function in terms of y. Well, integrate 1 in terms of y, what do we get? We get y, okay, plus 4xy squared. Okay, so x, just treat x as a constant, right? So we're going to integrate y, we'll basically raise the power by 2 and then we divide by 2, so a divided by 2 is 4. 1, we integrate with respect to y, we get y. Okay, and this one's going to be evaluated from 1 to 2. Okay, so as easy as that. Okay, but once we evaluate it, okay, notice that, and this is crucially important, so one should pay attention. These limits, okay, we're going to put those limits into where y is. Okay, we're going to put those limits into y. Okay, not into x. We did not touch x yet. Remember, we're holding x fixed. We're partial integrate with respect to y. So we're just going to put those limits in terms inside y. Okay, and so it's integrate 0 to 3, and basically the function that we get, okay, is 1 plus 12x. Okay, 1 plus 12x, and now we're going to integrate that with respect to x. Okay, we don't need to say partial integrate anymore because it's explicitly given in terms of x. And then you do your calculations, which you all should know, and I think we should get 57. Okay, so basically that is just partial integration put into action. No surprise at all. Okay, now just one fair bit I want to just mention. Okay, notice that I can rewrite this in another way. Okay, what I've done is just basically take the same function, okay, and I have just changed the order of integration. Okay, change the order of integration. Right now, I'm partial integrating with respect to x first, okay, and then I'm partial integrating with respect to y. Now notice if I change the with respect to terms, I have to also change the limits. Vitally important. Now right now, I must say that we're dealing with simple limits, okay? So basically, it's not, yes, it's still important, but when we move on to more complicated functions, you should be very mindful of that. Now this is summarized in a certain theorem. Okay, the theorem is this. Let R be the rectangle defined by the inequalities. X is between A and B, where A and B are obviously constants, and Y is between C and D. Okay, if the function x and y, function of x and y is continuous on this rectangle, then double integral of the function over the area R, okay, is given by this iterated integrals over here. Okay, and if I were to reverse the order of integration, they would give me the same result. But what is important is that this result is only applicable if R is a rectangle. Okay, now graphically what it means this. Remember I said that the volume of the solid that we wanted to find is bounded between the curve, okay, z equals to the function of x and y, okay, and this is the x and y plane. So if it's bounded by the x and y plane, and what bounds is the area R, and if the area R is basically a rectangle that's given by these limits like that, then it does not matter what is the order of integration that we will do. Okay, so basically this volume of solid. Okay, we can integrate first with respect to x, and then we can, and then y, or we can integrate first with respect to y, and then integrate with respect to x. Now this is just a second lesson, but later what will evolve from this is that, what about if R is more complicated, something like a shape like this. Okay, if R is not a rectangle, this theorem does not apply. Okay, if you change the order of integration, okay, it's gonna be different. It's gonna be a different result unless you do it carefully. But this only apply if x is between a and b and y is between c and d. Okay, so today's lesson is just about partial integration, how we want to hold one variable fixed, integrate with respect to the other one. Okay, and what we're gonna do now is that we're gonna look at more complicated examples. Okay, thank you.